Hello everyone, I am Dipali Chuk, Product Marketing Engineer for Texas Instruments High-Speed Amplifier Products. Today, we are going to show how we can achieve the specified datasheet performance for a SAR ADC driver when driven by the right operational amplifier. For optimum SAR ADC performance, the recommended driving circuit is an op-amp in combination with an RC filter. Without proper selection of the RF and CF values, the circuit could produce ADC conversion errors, or worse yet, cause the amplifier to be marginally stable. You can run into amplifier stability issues if you ignore the op-amp open-loop output impedance and gain bandwidth product. The optimized ADC driver circuit uses the op-amp to isolate the ADC from high impedance input sources. RF keeps the amplifier stable by isolating the output stage of the amplifier from CF. CF produces a nearly perfect input source to the ADC. For this case study, we are going to focus on our newest amplifier family, OPA2835 and OPA2836 in combination with our newest SAR ADC family, ADS7945 and ADS7946. The OPA2835 and 2836 is a family of ultra-low power, rail-to-rail output voltage feedback amplifiers. These amplifiers are available in single and dual versions. As you can see in this graphic here, OPA836, which is single low power with only 1 milliamps of quiescent current, 205 megahertz of bandwidth, rail-to-rail output voltage feedback amp, is driving the ADS7945, which is 14-bit, 2 megasamples per second, dual-channel micro-power SAR ADC. To calculate the minimum gain bandwidth required for driving any SAR ADC, we need to take into account its resolution in bits, which is N, and its acquisition time, TAQ. Let's see what is the minimum gain bandwidth required to drive this 14-bit, 2 megasamples per second ADS7945 with acquisition time of 80 nanoseconds. This is the procedure that shows us how to calculate the minimum unity gain bandwidth of the op-amp that can support the ADC based on its minimum acquisition time and our rules of thumb for the RC filter network and good op-amp stability. We first calculate the value of K, which takes into account N, that is, the resolution in bits for ADC. For ADS7945, this N is equal to 14. And then we calculate tau, which is the acquisition time of ADC over this constant K. For T acquisition is equal to 80 nanoseconds, the time constant comes around 7.7 nanoseconds. Following this, we calculate frequency, which is 1 over 2 pi tau. In this case, it is 20.7 megahertz. And finally, minimum gain bandwidth is 4 times this frequency, which is 83 megahertz. OPA836 with 1 milliamps of quiescent current and 205 megahertz of bandwidth would work great for driving this micropower ADS7945. The circuit here shows 2 OPA836 op-amps configured as a differential amplifier, each in the inverting gain of -1 with RF is equal to RG is equal to 10 kilo ohms. A 2.2 picofarads capacitor in the feedback helps to minimize gain peaking and noise. The two 4.99 ohm resistors and 1 nanofarads capacitor at the ADC input provide a single real pole filter to limit noise, and more filtering may be required depending on the application. For comparison, we took 2 sets of measurements, one with ADS7945, OPA2836 and 1000 ohms of source impedance. In essence, the ADC was not even being driven. For the second case, we dropped the source impedance from 1000 ohms to 10 ohms, which is the ideal input driver for this ADC. Now, let us take a look at the measurement results. This shows the measurement results of the first case where ADS7945 was not even being driven. As you can see here, at 10 kHz of input frequency for 100 kHz range, the SNR is 52.4 dB, SFDR is 60 dB, and THD is 56.8 dBc. In essence, the performance is really bad. Now, if you look at the measurement results of the case where ADS7945 is driven by OPA836 with source impedance being dropped to 10 ohms, you can notice the SNR jumps to 82 dB, SFDR to 103 dB, and THD goes to 102 dBc. In essence, the performance is very, very good, and one can match the specified datasheet performance for this ADS7945 SAR ADC when driven by OPA836. To learn more about ADC driver amplifier portfolio, and in particular the OPA2835 and OPA2836 family, please go to the URL shown on your screen. And if you would like, post a message on our online E2E community at e2e.ti.com. Thanks for watching.